Hello, welcome to week 4 where we're going to kick off physical water quality parameters with sediment. And first we're going to talk about some definitions, sediment sources and big picture sediment transport in the US, conservation of mass, the fact that sediment transport is natural and the standards as a result of that, quantifying sediment and turbidity as a surrogate, and temporal variability in sediment concentration and transport. So distinguishing between, there are 3 different categories of solids transport in streams: dissolved solids, suspended solids, and bed load. And the analytical definition of total dissolved solids, or TDS, is something that will pass through a 2-micron filter. In the world of chemistry, 2 microns is huge, and there are a lot of things that will pass through 2 microns that are not dissolved in the traditional sense. And we'll get more into that in the chemical section. But so things that are bigger than 2 microns are total suspended solids if they aren't bed load, which bed load is that the materials that bounce along the bottom and are in regular contact. So the things that don't bounce along the bottom regularly but stay in suspension and are bigger than 2 microns, that's total suspended solids, or TSS. So where do these solids that are transported by rivers come from? We can think about this in terms of upland sources. So when a raindrop hits the surface, there's a lot of force associated with that, and it can bounce sediment down a hill slope. If the surface the soils get saturated, or precipitation falls too quickly for it to infiltrate, you might get sheet wash running off over the surface. So this is evenly distributed precipitation running off. If that starts to get concentrated into small flow paths, then you could get rilling. And so as water gets concentrated and gets deeper and faster, it has more erosive energy, and you can start to move sediment and cause these rills, or these small valleys here. If rills get sufficiently large, they could cause gullies. Gullies are typically characterized as having a head cut at the top of them. This is a gully actively forming in Pocatello, Idaho, when this river over here had a debris jam and displaced the channel, the flow out of the channel. And it's running through this pasture. It's cascading off of this step here, or head cut, and there's a bunch of energy there that's causing erosion, and now this head cut is moving back upstream, and an immense amount of sediment can be lost in a single event like this as this gully forms. So there's kind of a stepwise process here, from sheet wash that's not very erosive, to rilling, which is much more erosive, to gullies, which are very erosive. So these are in-channel types of sources here, and another in-stream source is bank scour or slough. So if you've got this stream cutting back into this bank here, or bottom scour if it's moving material off of the bottom and down cutting. So these are the processes by which that sediment gets into the stream, or is to be transported. And if we look at this map from the USGS of the United States, the semicircles here represent millions of tons per year that are delivered to the oceans. And then the colors represent the milligrams per liter of sediment, the concentration in the rivers. And so a few interesting patterns here. If we look at the southwestern United States, we see darker colors indicating high concentrations of sediment in those streams. And so if we think about the precipitation in the Southwest, there's not much precipitation. And so there's not enough precipitation to keep healthy vegetation communities distributed across that landscape in a lot of cases. And then the nature of the precip, when it does come, it often comes in monsoons or intense rainfall events. So intense rainfall falling on landscapes without vegetation can move a lot of sediment off into the streams, resulting in these high concentrations. That's in contrast to the eastern United States, where there's more evenly distributed precipitation, and in general enough to maintain healthy vegetation across the landscapes. So although there's more runoff in the eastern United States, there is not as much sediment in it because the vegetation does a good job of holding the sediment in place. If we look at Alaska, then the northern portion of the state is covered in tundra, which is a thick vegetation mat that does a really good job of holding sediment in place. As opposed to the southern portion down here, where you've got these steep mountains with glaciers that are grinding up the sediment and producing these big sediment loads, for example, in the Copper River, producing the Copper River Delta, which is quite famous. So if we look at the Mississippi, obviously carries large sediment loads and delivers those to the Gulf, which creates the Mississippi River Delta. If we look at the Colorado River, though, we see these high concentrations of sediment coming off of these landscapes, and yet a minuscule amount of sediment reaching the Sea of Cortez here. And if we think about this in context of, so to get a lot of delivery of sediment to the ocean, you've got to have high concentrations, or important concentrations at least, and flow. And the Colorado lacks the latter. Very little, a trickle of flow reaches the delta at the Sea of Cortez here. Another interesting note is that, so the dams along the Colorado River are a very important sediment trap, which we'll talk about a little bit more in a minute. Another note here is that this hatched area on the Columbia is the increased sediment load associated with the Mount St. Helens eruption. I lived in Moscow, Idaho during that eruption, and we had to wear dust masks because of the extensive amount of ash that was deposited across the whole area that produced this big increase in sediment load to the Columbia. So one of the reasons that I talk about sediment first, I break down the water quality into physical, chemical, and biological. And sediment is handled first at the beginning of physical because it's maybe the easiest to conceptualize. You can visualize it, and it also obeys conservation of mass in a very clean way. So conservation of mass means that if you've got this river transporting something downstream, then through a reach you have flux in, which is the concentration of something times the flow or the discharge, and then you've got a flux out, and these two things are equal with accounting for storage. So if you get increased storage in a reach by grading or building a point bar, then you get a positive number for storage. And so you've got your flux in, you subtract that increase in storage off, and your flux out is smaller. So this is conservation of mass in very simple terms. And sediment obeys this more cleanly than things like nutrients or bacteria, for instance, that might die during the reach or be, in the case of nutrients, taken up by plants or something like that. So conservation of mass is a ubiquitous phenomenon in our environment, but those other parameters don't obey it in such a clean way because they can change their form. It's very important to note that sediment transport is a natural process. We have uplift of mountains, and then those mountains are degraded by erosion, and that sediment moves back to the sea. And so uplift by tectonics, erosion back into the sea is a very natural process, and the stream sinuosity and channel form that results in that natural process is ecology has evolved around that. So sediment transport is natural and very important in streams. And this raises an important point about water quality standards, that the Clean Water Act in its original form was a narrative, and it's a description of how water quality should be protected, that no increases allowed above naturally occurring levels of many things here that are going to cause harm or detriment to public health, recreation, to people or animals. So words describing the way the water should look. And that's as opposed to numeric standards, which are specified concentrations. So for arsenic, we can't have greater than 10 parts per billion of arsenic for drinking water for humans, or the risk of cancer gets too high. So Numeric standards are very convenient for a lot of things because it's cut and dry. We say, okay, you either meet the standards or you don't. Narrative standards are subject to interpretation. And this is important in the context of sediment because sediment transport is a natural process. And so a simple narrative standard for sediment might say no increases are allowed above naturally occurring concentrations of sediment or loads of sediment. So what makes a stream natural? How do we know what natural is? In the case of the Colorado River here, or the Green River actually, in Moab, central Utah, sediment transport is really important to point bar formation and to this desert ecosystem. So if we look across the United States, and then we expect to see different systems, different types of streams as a result of where we are. Looking at Montana, for example, one way to think about this is in the form of ecoregions. So the Middle Rockies ecoregion here, we know the streams there are going to be very different from those in the northwestern glaciated plains. And so ecoregions, in this case level 3 ecoregions, are based on geology, climate, and vegetation. And these black dots represent the Montana Department of Environmental Quality's network of reference sites. So this is one way to think about nesting reference sites within these ecoregions. And so you're not going to compare the sediment loads that we expect to see in a prairie stream with those that we see in a mountain stream. So thinking about comparing these sites to other streams in proximity to them is the way that we can figure out that natural background of sediment transport. So we don't say that streams can't transport any sediment at all, but that we don't want them to be transporting more than they're supposed to naturally. So if that natural balance gets out of whack, then there's all kinds of problems that we can get. A few listed here are aquatic habitat degradation. So if we look through this polarized lens at this sediment being deposited on the bottom of this stream, that can cause problems for salmonids that spawn in gravels. And so lay their eggs, and their eggs need oxygen among these gravels. And if you get this fine sediment deposited above the gravel, it can smother the eggs. Similarly, if cities get their drinking water out of surface water sources, or irrigation works where people are diverting water, lots of sedimentation can cause big problems. Irrigation companies spend a lot of money each year often cleaning out canals from sediment issues. Another big type of impact is surrounding dams. If you've got a big sediment load coming in this case the Glen Canyon Dam on the Colorado River, you have a lot of sediment coming in upstream, but that has all settled out by the time the water has gotten to the dam here, and we are losing storage capacity of these reservoirs slowly through time, or in many cases quickly, as that sediment drops out and reduces the size of the pool. The flip side of that is that downstream you've got this water flowing out that's completely starved of sediment and can cause a lot more erosion downstream on the river. So if we think about sampling for sediment, one important consideration is this velocity profile cartoon that we might think about. So faster flow in the deeper part of the stream and towards the cut bank here. And so to address that, often we'd come out and collect a grab sample, but in some streams you might get very different concentrations of sediment across a channel width. And because sediment is always going to be trying to settle and it's just going to be lifted back up by turbulence, you might get a lot higher concentrations of sediment down near the bottom of the stream than near the top. And so to deal with that, we might think about depth and width integrated sampling. This is an example of a DH81, which is basically a handle with a sampling bottle that's got a nozzle on it, which is got a small opening which lets a small amount of water in at a time, a constant and small volume. And you can walk out across a stream and raise and lower this rod to let sample into the bottle slowly. And so you can get a depth integrated sample by raising and lowering the sampler, and then you can move across the stream to get a width integrated sample. And so if you want to get a really accurate representation of sediment moving through a stream, especially in really big rivers that might have very different flow across their width, then this type of sampling is important. In cases, this is where you can wade. If you can't wade, then you might use a similar piece of sampling equipment deployed from a bridge. So exactly the same equipment here, just on this a rope lowered device here. So once we get that sample, a lot of times these sample bottles will be poured into a bigger sampling container or churn to get a smaller sample to come back to the lab with. And once you come back to the lab, you're going to take that sample, and I said that it's everything that will pass through, that will be retained on a 2-micron filter. So you take your filter that's got a pore size of 2 microns, and you pour your sample in, and you filter it, and then what's retained on there, you dry it and weigh it, and the weight change of that sediment is your mass. And so the units of suspended sediment are what? Mass per volume. So we also need to measure the volume of our sample, and then we've got our mass per volume, which gives us our total suspended solids number. So this is a pretty straightforward way to make a measurement, but it does take the time of collecting a sample, bringing it back to the lab, and running through this process. So if we come out to a stream and at high flow, we expect to see highest concentrations of sediment at high flow. People who are fishermen understand this because streams get blown out in the spring. So this is a classic snowmelt hydrograph, and during this time of year the streams are blown out or have a lot of sediment in them, and it's not a good time for fishing. But as the flow starts to drop back off, the sediment levels drop, and the water gets clearer. And the reason that we have such high sediment, so if we added another axis over here for sediment, we might expect the sediment concentration to parallel the discharge in the stream. And that's because at the highest flows, the stream has the most energy to transport sediment, and also at the highest flows, you might have the most overland flow moving into the stream, carrying those sediments in. And so that concept is depicted in this graph here, which is a relationship between flow and sediment concentration. So at the lowest flows here in Big Coulee, we've got really low sediment concentrations, whereas when the flow gets high, we get a really large sediment concentration moving downstream. And it's important to note that, so this relationship here gets an R squared of 0.99, so 1 is perfect. This is a really high R squared, but it's important to note that this is a single point causing a lot of influence on this line. If we had more points up here, we certainly would see some scatter around that. And so the p-value, while the R squared here, the fit of the line is very good, the significance of that, which we'd think about in terms of a p-value, the p-value would be high, indicating that this is probably not an extremely significant relationship. It's probably a true and important relationship, but with this few data points, not extremely significant. Another thing to think about with, so this is a surrogate measure, right? We are regressing these two things against each other. We're saying that flow has a relationship to sediment concentration based on what we described here. Turbidity was traditionally measured with a Secchi disk, and so traditionally measured in lakes, this is a checkered pattern on a disk that is lowered into the water until it just disappears. So at that point, right where it disappears, that is your Secchi depth. Okay, and so this is a tape measure that it's being lowered on. You read it there, and it tells you the depth, or the Secchi depth at which the disk disappears. So large numbers mean that the water is very clear and you can see it to a great depth. Very small depths mean that it's cloudy. Another way to measure this is with a sensor, a light sensor, where you shine a light into a water sample and a light detector measures how much of it is bounced off. And the units for this are nephelometric turbidity units, or NTUs. And the amount of light that a water sample bounces off, or the cloudiness of that sample, has everything to do with the suspended solids that are in the sample. And so as a result, we can create relationships like this one, where we expect the amount of a suspended solid in the sample to translate to a turbidity unit. And this relationship is going to be different for different watersheds, and it's a result largely of the type of solid that is causing the turbidity. So clay is going to reflect light differently than sand, than organic matter. So depending on what is making up those suspended solids, it's going to reflect the light differently and give you a different NTU. And that's why you would expect to see some of this scatter. And even within the same watershed, because different parts of a watershed could be contributing sediment of different kinds at different times. But this can be a very useful tool. And if we look at the paper that you're going to read for this week, this is the Little Bear River watershed in northern Utah. This is actually the valley that I grew up in, which has mountainous headwaters back here, and then increasingly agricultural moving downstream. And they have deployed a number of these turbidity measurement stations. Two of them are talked about in this paper, with the headwaters being more forested and downstream being more ag-influenced. And so they have gone out and collected sediment samples at the same time, at the same site, where this sensor is measuring turbidity continuously every hour or something. And they have built a similar relationship to what we just looked at between turbidity and suspended solids. And so with increasing suspended solids, the turbidity concentration increases, and we can make a regression line here and predict suspended solids based on turbidity. And so this graph shows the total suspended solids through time as estimated by turbidity. And this is a really interesting graphic if we look at the dots representing the observed values and the line representing the estimated values. And so we expect to see, this is a snowmelt hydrograph, so in March each year the discharge goes up, and we see every year these recurring high sediment loads in the spring that we'd expect because of what we described before of seeing highest sediment at highest flows. But there's a lot that is not predicted by those relationships. This is a fall event that had a huge sediment load come off, and that is not predicted by that simple model of spring snowmelt time frame being the highest sediment concentrations. This number of samples that they collected is extremely high. They collected a lot of samples for this study, and they still completely missed this event. So these spikes that happen quickly, and especially if those are happening at high flows, huge amounts of sediment could be coming off then, and a regular grab sample approach, if they're coming out every month to collect samples, they're going to miss a huge amount of what's going on as they're trying to estimate the total sediment load for this watershed. So we'd have completely missed these with regular grab samples. They did a pretty good job in the spring of 2006. They collected samples up here and distributed well across this increase in suspended sediment. But they completely missed that event. They completely missed this high flow. They completely missed that sediment event. So these likely associated with heavy precipitation events, where you have some big limitations, even with that sediment rating curve approach that we talked about. So this is the third surrogate measure approach that we've talked about. The first was in discharge, thinking about stage as a surrogate for discharge. Next A few slides ago, we talked about flow as a surrogate variable for predicting suspended sediment, and now finally turbidity for predicting suspended sediment concentrations.